In this video, I want to go over a simple example of how you use Darcy's law to calculate the amount of groundwater flow. And we're going to use all three versions of Darcy's law that I showed you before. The two versions involving discharge and specific discharge of the Q's, and the version involving the interstitial velocity or the velocity of a water molecule, V sub I. Just remember that the discharge in terms of dimensions here, discharge is in dimensions of volume per time. The specific discharge and the interstitial velocity, these are both in dimensions of length per time. So to show you how this works, let's start with a simple, really simple example. So what I've tried to draw here is a cliff face on which a horizon is exposed. This horizon is one layer of an aquifer. Let's assume it's a confined aquifer, and it's exposed along the cliff face. And water is moving through that aquifer, and it is going to be dripping out across the cliff face. So water is going to be dripping out like this from the cliff face and falling below. And maybe we want to collect that water and use it to, say, irrigate something. So we want to calculate then the discharge Q of water that is coming out through here. So we want to calculate this. Oops. We want to calculate the discharge Q that is coming out of that cliff face there. So we want to calculate this volume of discharge here, Q. And we're going to use Darcy's law. So here's what we know about the problem. We know that this exposure that the water is coming out of this cliff, the horizon the water is coming out through, has a thickness of 3 meters, and it is, in this dimension here, it is 500 meters wide. So it's a half a kilometer wide times 3 meters high. And that will give us our cross-sectional area. We also know the hydraulic conductivity of the aquifer is 12 meters per day, and its porosity is 0.20. And then finally, we need to know something about the driving force for flow. So what we're told here is that the head difference, if we, for example, measured the head right here, right at the face where it's coming out, and somewhere up gradient over here, that this head difference between those 2 points is 2 meters. And the distance between these two would be 1,000 meters. So the hydraulic gradient is going to be 2 meters of head loss per 1,000 meters. So we're just simply going to plug into Darcy's law. Let's write it down here. With K equal to 12 meters per day, the area here is going to be 3 meters times 500 meters, which is going to be 1,500 meters. And delta H is 2 meters, and delta S is 1,000 meters. And we plug in, when we plug into this equation, we get that the discharge Q is equal to 36 cubic meters per day. So we could use that, then calculate if that's enough water, for example, to irrigate crops or whatever we want. Okay, that's the big Q discharge, 36 cubic meters per day. If we want to get little q, we merely need to divide that. Little q, remember, is equal to big Q divided by the area. So we just take 36 cubic meters per day divided by the 1,500 meters squared. And when we do that, we get 0.024 meters per day. To give you perspective, that's about 2.4 centimeters per day. So that's specific discharge. Now that doesn't really have much meaning to most people. What would have more meaning is if we could calculate, which we will do next, the interstitial velocity. So to calculate the interstitial velocity, we're going to use the expression that the interstitial velocity is equal to the specific discharge divided by the porosity. So that's going to be 0.024 meters per day divided by 0.2. That's the porosity. And that is equal to 0.12 meters per day, which again is about 12 centimeters per day, or if you're not used to centimeters, but English unit, that's about 3 inches per day. So that's as fast as water is moving within this aquifer. And hopefully it strikes you that that's really slow. And that's kind of typical for the rates of water movement driven by hydraulic gradients that occur in the groundwater zone. So to conclude our little exercise, we can calculate from this problem that the discharge of groundwater through the face exposed is 36 cubic meters per day. We might use that to calculate how much water this seepage could provide. We can also express that as a specific discharge of 0.24 meters per day, or we can express this as a velocity of that a water molecule would move, and that is 0.12 meters per day. All of these describe the same thing. They describe the speed, I should say, in which water is moving through this unit, the rate of groundwater flow, using, again, Darcy's law. So this is an example of how we use Darcy's law to actually come up with numbers that describe how quickly water is moving through a geologic unit.